Last video, we derived distributions the long way. Chase the event, integrate to a CDF, then differentiate. This video adds a single assumption, differentiability, and the integral disappears entirely. First, we build the change of variables formula, which takes the density of x straight to the density of y, and see why the slope of g is the exchange rate between the two axes. Then we let it work. An affine map of a Gaussian stays Gaussian, and when g folds the axis onto itself, every root of g of x equals y pays its own share. Start where last video left off with one new assumption: g is differentiable and strictly increasing. That buys invertibility. Every y now comes from exactly one x, so x equals g inverse of y is a genuine function, and last video's formula loses its sup. The CDF of y at y is simply the CDF of x at g inverse of y. Now differentiate both sides with respect to y. The chain rule hands us the density of y, the density of x at g inverse of y, times the derivative of the inverse, the rate dx by dy. That derivative is not a technicality, it is the whole story. Take a thin strip of width delta on the y-axis and pull it back through the curve. Where the slope is shallow, the strip pulls back to a wide interval of x values, so plenty of probability funnels into that band of y. Where the slope is steep, the same strip pulls back to a narrow interval, and hardly any probability lands there. The derivative is the exchange rate between the two axes. Probability is conserved, so the density must be rescaled by exactly how much the map stretches the axis. Substitute x for g inverse of y, and the result reads cleanly. For a strictly increasing g, the density of y is the density of x divided by the slope of g at x, and the slope is positive, so the density stays positive. What if g is strictly decreasing? Then g of x at most y means x at least g inverse of y, so the CDF picks up a 1 minus, and differentiating produces a minus sign, exactly canceling the sign of the now negative slope. One absolute value absorbs both cases. When g is differentiable and strictly monotone, the density of y at y is the density of x at x divided by the absolute value of the derivative of g, with x equal to g inverse of y. This is the change of variables formula, the workhorse of derived distributions. The recipe now has just 3 moves: invert, differentiate, and divide. It even collapses last video's channel fading example. The Rayleigh amplitude squared took an integral there. Here it takes one line, and the algebra folds down to 1/2 e to the minus y over 2. Same exponential, no integral. Time to let the formula work. Let x be a standard Gaussian, the bell curve with density e to the minus x squared over 2 divided by the square root of 2 pi. Let y equal ax plus b, an amplification and an offset with a non-zero. The map is affine, so inverting it is arithmetic. X equals y minus b over a, and dx by dy is 1 over a. Feed both into the formula. The density of y is the standard density evaluated at y minus b over a divided by the absolute value of a. Simplify and look at what came out: a Gaussian with mean b and standard deviation, the absolute value of a. The density shifts by b and stretches by a, but the silhouette never changes, only the labels move. The same progression works for any Gaussian input. An affine function of a Gaussian random variable remains Gaussian. Amplify a noisy channel, add an offset, and the noise keeps its distribution. Monotone maps are the friendly case. A real g can wander, rise, fall, rise again. As long as it is differentiable with finitely many local extrema, it is monotone piece by piece. So pick a level y and collect every x where g of x equals y. Each root sits on its own monotone piece, and each piece obeys the formula we just built. Add the contributions. The density of y at y is the sum over all roots of the density of x at that root divided by the absolute value of the slope there. The discrete world summed masses over the same preimage. Densities do the same, with the stretch factor that masses never needed. Watch it in action. Sample a sinusoid at a random phase. X is uniform between 0 and 2 pi, and y equals the cosine of x. For y strictly between -1 and 1, the level line cuts the cosine twice, once at arc cosine of y and once at 2 pi minus arc cosine of y. The derivative of cosine is minus sine, and at both roots its magnitude is the square root of 1 minus y squared. Each root contributes 1 over 2 pi times that root. Together they give 1 over pi square root of 1 minus y squared. Plot it and the shape is striking, a U. The density piles up near plus and minus 1 because the cosine lingers near its peaks. Shallow slope, wide pullback, heaped probability, the exchange rate at work. The key idea of this video: a differentiable map turns densities into densities. Divide by the slope and sum over the roots. Next, we aim this machinery at the CDF itself and turn it into a recipe for generating random variables.